So at what temperature is the resistivity of silver equal to resistivity of copper? We could even ask like those weird questions we asked in the very first section. At what temperature is the resistivity of silver the resistivity of copper to the power 1.5? You know, those the questions that we asked for the temperature scale. So maybe you had some reason why you want to warm the silver and make it a certain ratio of the resistivity of copper, some reason, and then you could warm it to that temperature. So if we want them to be equal, then you just say, okay, use this equation right here, right? This one, and then put the values 1.724. Okay, so resistivity of 0 of copper, 1 plus alpha copper, T minus 20. Resistivity 0 of silver, 1 plus alpha silver, T minus 20. So then this one, the silver was, no, copper was 1.724 and 1.59. 1.59, 1.724. So remember, copper was slightly more resistive. Okay, so is that what you got? Row 0
Yes.
of copper, 1.724. And then this is 1 plus 4.29 times 10 to the minus 3, T minus 20, 1.59, 1 plus 6.1 times 10 to the minus 3, T minus 20. Now here, the 10 to the minus 8 and the 10 to the minus 8 cancels. So I don't need them. But here I can't cancel the 10 to the minus 3 because it's added to 1. Yeah, so you see this one should be able to catch up to that one because the alpha is bigger, so its resistivity is increasing faster than the copper's. Okay, I think this is a time for Wolfram solver. We haven't used this for a while. 724. So I'm just choosing to, instead of write 10 to the minus 3, just take the decimal back 3 spaces, and then 1.59. 1.61 X. Okay, that's it, right? Okay. Oh, I think I saw it, 78. Yeah, 78 Celsius. They're the same. Yeah, that makes sense, right? So the temperature starts at 20. So if you heat it by like 58 degrees Celsius, it's already caught up. Okay, how about D? Some random condition. So then we want the silver to be 1.5 of that. So basically this whole thing would be to the power of 1.5. Then I'm going to have to heat it more, right? The more I heat this, the more it's going to overtake that, right? So in question B, we just do the whole thing, but then put a 1.5 there. So it's probably going to be something in the 100, I'm assuming. 100 Celsius, 100 something Celsius. Then I could say, put parentheses, put another one to the power 1.5. So there's only complex solution?
I think you put a lot of parentheses in the beginning.
Let's see, 1.72. This one closes this one. This one closes this one.
Oh, no.
No? Maybe, so that's telling us that that condition can't be satisfied. 1.7. Let's see, can it be? Yeah, because the more I heat this, the more it's going to start overtaking that one. I think it should work. Let's see, what if it was 1.2? No. One 1.1 is doable. 395 Celsius. You know why? Because they're, I guess it's telling us that at the rate that it's overtaking it, it can never be more than like 1.1 times greater, because they're both straight lines. You see the idea? So this is increasing linearly, but it's true it's increasing slightly faster rate. So graphically, it's almost like you're looking at two functions. This guy initially starts out lower, but it's increasing at a faster rate. And then the resistivity of this, so if we plot it, let's say this is 20 degrees Celsius. This is, let's say something like this. I'd always think of it graphically. So if this is the temperature T, so this is 20. At 20, the resistivity of the silver is 1.59. And the resistivity of the copper is 1.724. But the copper's growing slower. And then this one's growing like this. So we notice that this one at 78 degrees, they're the same, you know. You see? So it's telling us that if you take the ratio of this to this, you might never be 1.5 times, well, in other words, this one cannot be this to the power of 1.5. You know, this can not be this to the power of 1.5, but it can be this to the power of 1.1. You see, so the condition cannot be satisfied that this function is this to any random power. Yeah, I mean, they are getting further apart, but it could probably be like this. So of course, if you were to get the 1.5 power, you would say the answer is no answer, 1.5. But 1.1 does exist. There's two answers, huh? There's two answers that satisfy the 1.1, 395 and 759 Celsius. Or you could even say, at what temperature is the silver's resistivity a certain value greater? Let's say 0.05 greater than the, yeah, the silver's is greater by 0.05. Let's say, is that going to come out? Oh, okay, then it's at 99 Celsius. Yeah, then it's at 99 Celsius. So in this case, what you're saying is you want the difference of this, to be 0.05. You see, not so much that it's this to some power, but just the difference of the two graphs. And it's telling you at 99 Celsius, that condition will be satisfied. Okay, so you can see you can put any kind of condition there and then solve for it, but not all the time are you going to find real solutions. Okay. Any questions on that so far? So we've covered voltage, current density, resistivity, conductivity. That alpha was called the temperature coefficient. Alpha is called temperature coefficient. So the units for the alpha should be 1/Celsius. It kind of reminds me of the almost this equation, the length expansion. Just thought of it, because that was also 1/Celsius. But it's not really that related. This is telling you how much something expands, and then this one's saying how much its resistivity increases when you increase the temperature. Oh, the next thing is to derive the equation for the resistance of a cylindrical wire. So let's say you have a wire like this,